In this section, we are going to talk about calculating the training and validation set losses. So what does that mean? So in the previous section, we talked about the cross-entropy loss, which is a measure of how good the generated text is that our model generated. But in the previous section, we only calculated this for a small sample text. Now we are going to calculate the cross-entropy loss on the whole training and validation set that we are going to generate for the model training. So again, the cross-entropy loss, how it's calculated, it's between the logits, the outputs of the model, and then the target token IDs. So the target token IDs tell us essentially what are the tokens that the model is supposed to generate. And if the target token IDs are associated with a high probability score when we apply the softmax to these logits, which happens internally in the cross-entropy function like we talked about. But what I'm trying to say is ideally we want the model to output high probabilities for those token positions in the vocabulary that are associated with the target token IDs. And only then, if we have these high probabilities, the overall cross-entropy loss will go towards 0. So ideal case, it would be around 0, which means that the model outputs very high probabilities for the correct tokens. So that's our goal. Right now, it's very large. So it's 10.79, which is actually very, very large. So we want to reduce this number towards 0 in the process of the model training. But before we train the model in the next section, we want to first apply this calculation to the training set that we will be using for training the model. And here, specifically, we will be using the same training set that we introduced in chapter 2, the verdict by Edith Wharton. So just to give you the brief overview where we are in this chapter before we get to the code. So we talked a bit about text generation. We computed this cross-entropy loss in the previous section. Now we are applying this cross-entropy loss to the training and validation sets. And then later in the next section, we will be actually training the LLM finally. And then we will talk a bit more about more advanced text generation strategies. So we had a very simple one. I will add some sampling procedures to that one. We will also then, of course, save and load our model because, training might take a long time. So it would be nice if there's a way that we can save the model and load it later so that we don't have to retrain the model every time we want to use it. And then I will also show you how we can load the pre-trained weights from OpenAI into our LLM architecture. But let's talk first about calculating the training and validation set losses. So like I mentioned before, for this we will be using the verdict from chapter 2. And so here it's just boilerplate code which will load the verdict. If it's not already on your in the local folder here, then it will download it from the internet. So here in this case from my GitHub repository. If it is already in a file called the verdict relative in the same folder relative to this notebook, it will just open the file. So there's nothing really interesting here. It's just loading the file. It's never a bad idea to also just double check the dataset to make sure it's loaded correctly. If this were a bigger data set, this would be very cluttered and very, very large. So maybe it's also not just a bad idea to only print a few characters. So we can see this text looks okay. It's loaded correctly. There's no error or anything. So that is our training set. Also just like a sanity check, we can calculate the size of the training set again. So the number of characters in the data set. And also the number of tokens. So here using the tokenizer, the tick token tokenizer that we used before, we can see it's 20,000 characters and 5,145 tokens. So next, what we are going to do now is we are going to divide this into a training subset and a validation subset. So I should have a nice figure on this here. Here. So suppose this is the verdict dataset, this whole thing here. And what we want to do is we want to divide the dataset into a training portion, here the large box at the top, and a smaller validation portion. So the training portion is what's used to train the model, and the validation portion will be used to evaluate the model during the training to get a rough idea whether the model is overfitting to the training set or not. But we will get to that when we implement the training function. For now, maybe just think of it as dividing our data set into two portions. And what we are going to do is we are applying this procedure to each of the portions, of the two portions. I'm only showing it for the top portion, just, because there's not that much space here in this figure. But all these steps, they will be also applied to the validation portion at the bottom. But yeah, looking at one of these portions, in this case, the training portion, what we are doing here is we are subdividing the training set into these little boxes. So the box here has a size of 6. Why 6? That's so I can fit it into this figure. But yeah, if you consider our original setup, we have a context length of 256. So this is the context length, how long each training sample is that the LLM receives. We would make it 256 in our code because, yeah, it's of course better to have larger context sizes to train more efficiently. But here in this case, because the figure gives us limited space, I'm using a batch size, a context length of 6. So you can see the first 6 tokens are contained here. And this is like just a list of the raw tokens. For example, if I go here, let me see. So this should be this list here. It's a very long list. So maybe let's immediately again get rid of it so it's not too cluttered. But yeah, what you are seeing here, this list is essentially this list. And now we are subdividing it into training samples. So the first 6 tokens will be the first training sample. Then the second 6 tokens will be the second training sample, and so forth. So here you can see we organized this in a tensor where we have 6 columns, so 6 tokens per training example, and each row is a training sample. So that's basically what you're looking at here. And then what we are doing is we are subdividing the whole data set here into batches. So here I'm using a batch size of 2. So the first of 2 training samples are in the first batch, 2 training samples are in the second batch, and 2 training samples are in the last batch. And what you can also see if you pay close attention is that the batches are shuffled. So here, for example, you can see that the first row does not correspond to the first row here. It's like the 4th row or something like that. So because we use shuffling in our data loader, like I explained in chapter 2. And yeah, and this is the pipeline for going from text into a data loader implementation to obtaining these batches that we will use for the training. And we will also use the batches to evaluate our model, because it would be very expensive to pass the whole data set all at once into the model. So we will be evaluating the model by iterating also over these batches. But maybe this will become more clear once we implemented this. So the next step would be loading just a data loader that we implemented in chapter 2. So here I have my previous chapters file where I have all the different functions and methods and classes we implemented in the previous chapters. And one of them was in chapter 2, the create data loader version 1 file or function. And so I'm loading it here. We'll be using it in a few moments. Then I'm saying, okay, we will use 90% of the data for training, and then the remaining 10% will be used for the validation. So what you're seeing here is, I need to make this more clear. What you're seeing here is the number of characters that make up the first 90% of the data set. So if we have, let's say 0.9, then this is the number of characters that we see up here. So if I execute this, you can see the first 18,431 data points will be the training data set. So if I have text data here, what will happen is that this will be our training data set, and then the remaining tokens or characters from 18,000 till the end will be our validation data. And so that is what you are seeing here. So that's all that's happening here essentially. So we have now a training set and a validation set. And next we are going to initialize the data loaders. So let me just copy it here so I'm not making any typos. And this is the same that we had in chapter 2. So we have the training set, and the validation set. So we have 2 data loaders, and we use a batch size of 2, similar to the figure, the context length and the stride. And so if we would set that to 6, it would look like here, right, where we have context size of 6, and then we have a stride of 6, which means moving 6 positions over and getting the next 6 and so forth. Except in our case, this is a hyperparameter that we have set to 256 up here. Yeah, and then we drop the last batch if the number of the data set size is not evenly divisible by the number of batches. And then we set the shuffling, and that's essentially it. So there's nothing really new compared to what we have covered in chapter 2. Yeah, and then what I usually like to do is I like to iterate over the data set. So if you have a very large data set, I would probably do it like this. And so this will just make sure that there are no errors in the dataset, where it iterates smoothly through the dataset. And you can see the first tensor here is the training set tensor, and this is also the input IDs, and this is the target IDs. That's the way we set up our data loader. If we go back here to the dataset, you can see we have the input IDs and the target IDs. And so this looks good. So we have a batch size of 256 tokens each. If you want to, you can also, because it's a relatively small data set, you can just iterate through all of them. And so we see how many batches we have. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 batches. Then what we can do is we can do the same thing for the validation set. We can see we only have one small validation set. So that's like really, very, very small data set, so that the training doesn't take forever. Remember, this book is for educational purposes, and we will be loading the OpenAI weights also later on, so you have a more capable LLM. Here, it's really just more for illustration purposes. I wanted to print a few more statistics here. And so what I'm doing is, remember this number of elements method, which computes the number of elements, the number of tokens in each of these, right? So if we have x.shape, we have 2 times 256 tokens. So we can compute this as follows. So this is the number of tokens. So here I'm just computing brute force the training tokens we have in our data set by iterating through it. And I'm doing the same thing for the validation set. So let's print the number of training tokens and the validation tokens and add them up and see if we get roughly what we have up here. So just to make sure that, the numbers still make sense. It's a good way of sanity checking. So what we can see here is that we have 4,608 training tokens and 512 validation tokens. This looks okay, of course, compared to what we have computed before, but this one is a bit suspicious. So when we add up the training tokens and validation tokens, why don't we get the 5,145 we had earlier here? And so there are 2 reasons. So the first one is, if we look at this figure again, what we are doing is we are subdividing the dataset into these context length long chunks. But then if this dataset is not evenly divisible by the context length that we define, there will be a leftover chunk at the end that doesn't really fit this. So if we drop this, then of course we will not have so we will have dropped some of the tokens, the last, in this case, 25 tokens, because they're not divisible by the 256. And the other one is also when we consider the training loader and we drop the last one, if the last one, or if the number of batches is not evenly divisible by the batch size. But yeah, so that is why we are losing some tokens here, but it's not a bad thing. We want to really make sure each batch has the same size so that we don't have any weird loss spikes during the training. And in reality, when we're training deep neural network, we have trillions of tokens usually, so it doesn't really matter if there are a few tokens missing. It really, really doesn't matter at all. We have so much training data, this is just like a drop in the bucket. Okay, so this looks good then. So we have 5,120. Now, the goal of this section was to compute the loss of the training set or the loss on the training set and the validation set. So how are we going to do that? So I have a few functions here, 2 functions. They look a bit complicated, but if we go through them in a, I would say, strategic manner, then I think it should hopefully make sense. So maybe starting with this calculate loss batch function. So this one is, I will get to the details later, but this on a high level is a function that computes the loss on one of these batches. So here we are iterating over the training order, and we get the input batch and target batch for each iteration. So this is one input batch and one target batch in our training order. Essentially what we are returning here, right? Okay, so this is computing the loss on one batch, the calc loss batch function, and the calc loss loader function will apply this calc loss batch on each of these batches in an iterative fashion. So it will iterate over the data loader. That's essentially what's happening. So, and in each calc loss batch function here, what we are going to do is we are computing the cross entropy loss, similar to what we have discussed in the previous section, between the layer outputs, the logits, and the target batch. So this is exactly what we have done in the previous section, now applied, instead of a prompt, applied to a batch. Now you see this here, this line. What is happening here? So this one is transferring the data to a device. And we have this device here too, which gets passed down here. Now, what it does, it's if we have a model sitting on a certain device, so maybe let me just show you an example. So if we have this line here, for example, this will check. So your computer may have a GPU, a CUDA GPU. So a CUDA GPU is a GPU by NVIDIA that supports the CUDA library, and CUDA is, you can think of it as a programming language like C++ for NVIDIA GPUs. And if you just execute this one, you can essentially double check whether your computer supports this, if it has a GPU and supports CUDA. In my case, it returns false because I'm running all the code here on a MacBook Air, which is an Apple device, so it doesn't have a GPU, of course. But if you want to, there is an equivalent. It's called MPS. It's called MPS stands for Metal Performance Shaders, I think. It's like an equivalent by Apple for CUDA to utilize the what is it called? Apple Silicon GPU, essentially. So in my case, I have this Metal Performance Shader support. So you could technically replace this, in my case, by this one, and it will be faster than the GPU. Sorry, not the GPU, the CPU. It will be faster than the CPU on this machine. I'm still using the CPU here though, because it's a bit more stable. When I started writing the book, I tested all the code with MPS, CUDA, and CPU, and I got similar results on CUDA and CPU, but I got slightly different results when I used MPS. That was back in PyTorch 2.0. Over the course of the last few months, when they released PyTorch 2.6, I noticed it became a bit more stable. So you can get similar results now with MPS that you could get with CUDA and CPU. But sometimes you get some rounding errors because it's a bit newer, the MPS support. So, but yeah, even though it's slower, just to make sure I get the same numbers you might be getting, I'm using a CPU here. And so what is happening here is that we're transferring the data, the input batch, to the same device where the model is sitting on. So what we might do is we want to, for example, transfer the model to the target device. In our case, this will not do anything because by default, the model already sits on the CPU. But if you're so this is why I like to do the semicolon, by the way, because it outputs the whole architecture. But if your computer supports CUDA, then this will transfer the model to the CUDA device, or if you chose to use MPS, to the MPS device. And then we have to make sure, though, that the data is also transferred there, because otherwise you have data sitting in the CPU memory and the model sitting on the GPU memory, and then, yeah, they won't be able to easily communicate. So we have to make sure they sit on the same device, and that's essentially what we're doing here. Here, what we are doing is just some initialization of the loss, because we will be computing the loss in an iterative fashion. So for each batch, we will get the loss added up. So we have the plus equal, so we add it up to the total loss, and then we divide by the number of batches. It's just like an iterative way we compute the loss, and then just some baseline checks. If there's no batch in the data loader, then it will just generate a nan, not a number. Yeah, and otherwise we can define the number of batches here. So for example, to make computing cheaper, if we have a large data set, we only want to test something, we can enter 2, then we'll only compute the loss over 2 batches. But if we set this to none, it will use all the batches. So length data loader, for example, if we have length train loader, it will give us all the batches here. In this case, we have 9 batches. Yeah, so this is what this the combination of the two functions are doing. And this will then calculate the loss. So let's do it. Let's compute the loss here on the training set and the validation set. So I'm setting the manual seed because there's a shuffling involved, but it shouldn't make a difference actually for this calculation here, because here we are going to iterate over all the batches anyway. If we had a num batches 2, you might get different results because the 2 first batches might be different depending on the random seed. Here, since we iterate over all of them, it should be, it doesn't really matter whether we use the random seed or not. Of course, we use our torch no grad, because otherwise we will be constructing this computation graph of the model in the background. And we don't need the computation graph just yet because we're not training the model. So this is just like an efficiency tweak. And then, yeah, we compute the training and validation loss using our calc loss loader function. Let's compute this, and this might take a bit because, yeah, oh, it's actually quite fast because it's iterating over the whole data set and then passes it batch by batch to the model. And we can see the training loss is quite large here. So it's about 10.98. It's approximately the same that we've seen on the sample prompt in the previous chapter. And this is because the model is not trained yet. Ideally, when we train it, we want to get that below 1 at least. So that would be pretty good. And by the way, before we go to the next section, I forgot to introduce the topic of perplexity. So there's a concept of perplexity, and this is just like another measure to measure the quality of the generated text. And you have maybe seen or heard about this before in the context of LLMs. And so the perplexity is measured as the exponential of the loss. So for example, if I have a loss value like this one, I can put it in here, and then the perplexity would be 50,900 something-ish. And so the perplexity tells us how unsure the model is for the number. It's the number of words. You can think of it as the model in the vocabulary is unsure about that and that many words. So how many words do we have in the tokenizer again? Actually only 50,000. So, you know, it's like a rough estimate. It should actually be around 50,000-ish. So I think if I make this a bit smaller, like you can see how sensitive this is. Yeah, so what it tells us, it's basically the model is unsure about any of the words or most of the words in the vocabulary. So in that sense, our model is not very good. It's not very trained. We have a high loss. We want to get this loss down to around 0 ideally, but realistically, maybe 0.5 would already be good. So it's unsure only about 1.6 words in the vocabulary, for example. So unsure means it doesn't really know at which position what word it generates. At any position, it might take any of the words in the vocabulary as being equally likely as the next word. And this makes sense because we haven't really trained our model yet. So the model doesn't really know what it should generate as the next token. So that is going to be the task of the next section, where we will be implementing the training function to teach the model to be more confident about generating the next token.
Get this book at Manning.com.